Okay, let's check out some functions and commands we will be using here. In class, we talked about this division operator deal, and we showed that, A equals 1/2, B equals 1/2 with the slant pointing in one direction or the other is going to give a different result. So if we run this, it says 0.5 and 2. So we can say this is 0.5 and this is 2. So we can see that wherever this slant is heading, whichever direction it's heading, is the direction of division, essentially. So pointing forwards of 2 says this is 1/2. Pointing towards the 1 says 2/1, right? So that's kind of weird. I don't know, quirk of MATLAB. Just get in the habit of probably using one or the other, whatever you're comfortable with. I would really suggest you use / for division. Okay, so what about this leading dot when we're doing stuff with these vectors? So let's say A equals 1, 2, 3. B equals like a column of 1, 2, 3. So if we were to do the output of this, right, we're going to see A is 1, 2, 3, right, and B is 1, 2, 3. But A is a row vector because it's separated by commas, and B is a column vector because it's separated by semicolons. So if we did A dot divided by B, we would see an output of a matrix, whereas if we did B transpose, it is a row vector, right? So what's going on is that we're starting with every element in A, right? 1, then we're going to compare that to everything in every column of B, right? So 1 divided by 1, 1 divided by 2, 1 divided by 3. That's in the first column. Second one is element 2 of A, right? So element 2 of A right here, this dot, is going to be divided by everything in B's column, right? So keep going and you get this matrix. However, if you transpose B first, right, you put this B transpose at the end, then B becomes another row vector and there's no columns. There's just one column, right? So 1 dot divided by column, or 1, 1, right? So in this case, let's say, let's spell it out for you. Say C is actually equal to B transpose. All right, so then we'll do C there, right? So you can see that C and A have the same dimension, right? They're 1/3s. You got one row, 3 columns. Got 3 rows, 1 column. So A and C have the same dimension, and they give resulting output in the same dimension. So in this case, it would be it would be first element in A divided by the first column in C, right? 1 divided by 1, 2 divided by 2, 3 divided by 3. Since there's no more elements in C, column-wise, you just get an output 1, 1, 1. Okay, so that's a little tricky in MATLAB. The other thing that is a little tricky, and let's just comment this, and I'll keep A and B like this. we can use the dot for other stuff, and we can ask MATLAB, hey, help. What else do I use a dot for? Right, and it's going to give you this output. If you just type in help and you type in whatever after help, it's going to be a summary of what that thing is. And it's going to say, hey, we can do array multiplication if you do dot times. You can do array power if you do dot to the power. Dot forward divide, back divide, forward divide, right? If you don't know what's going on with array multiplication, you can just click on this link, and it's going to tell you what array multiplication is. So, all right, so this help deal is pretty valuable. It's going to help you out. All right, so let's comment that. And let's try this whole power deal. So A dot power B. And let's see what happens to this output. So it's really weird. It gave us this matrix again, right? And that's because it's going to be 1 to the 1 power, right, is 1. 1 to the 2 power is 1. 1 to the 3 power 1, right? So that's kind of what we expected from, the lesson up here. But let's say it's not what we wanted. We actually wanted to have a row vector output. So we're like, oh, all right, let me just do transpose. So let's go D equals A to the power B transpose. Oh, that'll fix it, right? No, it won't. Doesn't fix it. That's because what it's going to do is this transpose the result of our output, A to the B. This is really weird because it worked for division. It worked up here, but it doesn't work for the power one. I don't know. Whatever. MATLAB can be weird, again. So what we need to do is tell it, force it to transpose B first. And we can do that by just writing this function transpose. And then now it has to go through this function transpose, get an output, and then it can do the rest. So let's see what the result is here. I forgot the R. Transpose. So now we're going to do 1 to the 1 power, 2 to the 2 power, and 3 to the 3 power, right? That's an expected output. Looking good. All right, so comment that, and comment that. All right, so what's going on with these other sum, max, mean, all these things when we talk about matrices? And I think we talked about this in the first lecture. So let's say A is a matrix, 1, 2, 3. So it's the first row of the matrix, second row of the matrix, 4, 5, 6. Third row of the matrix, 6, 7, 8. If we run that, you can see popped out the right matrix, except I actually wanted that to be 79. Okay. So there's the matrix A. Let's say we wanted to sum A. First thing we're going to see is that it goes column by column, summing every column, giving us a row vector. All right. If we wanted to do the sum of each row to get a column, we would get sum A in direction 2. Sum A in direction 2 gives us 6, 15, and 24. So this is the direction 2 is row-wise, direction 1 is column-wise, and MATLAB defaults to 1, direction 1. We can also do sum of everything in A just by saying all. All right, so 45 is a sum of all these numbers. What about max and mean and all that? Well, max, these guys have a little bit different code. All right, so max is going to compare the matrix here with the matrix here. So let's say A times 2. All right, so in this case, it's going to compare element by element, 1 and A, and then A times 2, so that would be 2. So the max of those two is 2. And next again, it's going to go to 2. It's going to say 2 times 2 is 4 on that element, and then compare that with 2. 4 is the max. All right, so obviously everything here is going to be the max. You're just going to get a matrix output that's A times 2. But let's say we wanted to just get the matrix, just get the max value in the same matrix, right? We don't want to compare with another matrix. In that case, we can just add an empty matrix right here, right? These little brackets, and then we can give them the dimension that we want to max on. So in this case, it'll give us the max in each column. So we would expect 3, 6, 9. Oh wait, sorry. Yeah, it would give us 7, 8, 9 because we're comparing the columns, right? We're comparing column 1, column 2, and column 3, and we're saying the max in each column is 7, 8, 9. But if we wanted to do the rows, right, we would get dimension 2, and then we would get 3, 6, 9. So our output is a column vector 3, 6, 9. All right, we can also do max of all just by typing in all. So max column-wise, dimension 1. Max row-wise, dimension 2. Max of everything, all. Okay. The special bit is that on some of these, you're going to need to put an empty matrix in because it wants to do a comparison like naturally. I don't know why. So when do you know that you got to put in this little special matrix? You can just type in help. Max in the help says, hey, look, I want to compare, I want to compare the largest elements taken from X or Y. That's like what max does fundamentally, right? If you want to do special stuff like we did, we can say determines the largest element of the full matrix X, right? We can talk about operating along a dimension DIM, right? That's what we did right here, 1 and 2. All right, so read these helps for sum, max, mean, on all, everything you probably be using. All right, so let's suppress all this stuff. Okay, we're going to create an array of equally spaced numbers. All right. So how we do this is we're going to say we want an array from, say, x0 equals 1. We want to end at, say, 100. Say it starts at 0. x0 is 0, x100 is 100, and we want to be spaced by say 20. So what we would do is write array equals x0 colon step x 100. So this says starting from 0, step this amount until you reach this number, and then put that array in A. All right, so if we run this, we get an equally spaced array of numbers from 0 to 100 spaced by 20. Okay, that's what this block of code does. All right. If we want to do that all in one, right, we already know that it's, actually, let me just press that. We can do this all in one without declaring variables just by saying 0 to 20 to 100. And that will give us the same result, right? So let's say this is B. All right, that gives us the same result. All right, so that's an array of equally spaced numbers. Now we want to create a linear spaced array between two numbers with n values. So let's say we wanted to do this idea again, but say the between 0 and 1. And we wanted to have 20 values between 0 and 1, right? You could say 1 over 20 is your step size, I guess. But an easier way to go about it is, say A equals linspace. So linspace takes in a number, x0, x1, right? And then the number of points you want between them. So this is going to be n. So in this case, A is going to be actually let's take n down to 5 so that we can see it easily. All right, so then we're going to have 5 elements between 0 and 1, right, that are equally spaced between each other. Always equally spaced because this is a linspace. There's other operations like log space, cosine space, these things that give you non-linear results. But linspace is your friend. It's going to help you create these vectors of time and things like that, right? So that's linspace. Let's say we want to plot sine of x in time or something, right? We can make x equals linspace from 0 to pi, or 2 times pi, right? With, let's say, 100 data points. And we'll do y is equal to sine of x. And we can plot this using plot, right? And when we do that, it's going to just pull up a figure of sine of x. And we can do things in this plot like make each data point red circles, right? So every data point is now a red circle. We can add a line to the data points. Now there's a line with red circles. Okay, so there's a lot of options in each one of these plotting functions. And again, figure out what's going on, we can just type in help, and it's going to give us a whole list of things that we can do with plot. Here's all the colors we can make. Here's all the types of points. Here's like the dashed line kind of things. All right, so we can also look at the documentation just by clicking here, and it's going to open up a whole new window, and we can now see examples and a bunch of things, right? So that is plot. Plot will help you when you're debugging outputs a lot. So now let's talk about reading an image. Now I have this runner.tiff, and in the homeworks, you know, I give you this code, imRead, right? If we run that, we get this variable s in the workspace, right? That is now an image. That image has 792 by 612 pixels and has 3 values for each one of those pixels, right? Those 3 values correspond to red, blue, and green channels. And it's in that order. So if we were to say, try to take out the red channel from S, we would say S of everything, every row, every column in the first channel, red, right? R, G, B is 1, 2, 3. So this is red. Right. So if we were to do the next bit, IamShow of S gives us runner.tiff, right? It's gonna, if we run this, it's gonna pop up a figure and it's gonna show the runner with all the points. If we show S red, it's gonna show just the grayscale value of the red points, right? The green background went away, the black went away, everything went away except for stuff that have red values in it. If we were to look at blue, let's go. So we got red, blue, and green. Let's image show red. Okay, so we're going to make a new figure, image show red, make a new figure, do blue and green. Okay, so here we have the red channel over here, the green channel, and the blue channel, right? And so now let's say we wanted to extract, actually, sorry. Image SC is a different type of process, right? So let's look at the difference what image SC versus image show does. So image SC is always going to give you a nice image of anything that's not, you know, multiple matrices. So we can't do RGB, right? We can only do something that's a 2D matrix. So 792 by 612, you know, that's S blue, S red. We can look at those things. But it's going to give us this weird colorized output, and it's called a color map. and we can see that the values corresponding to these colors are from 0 to 255. So we can also click over these. You can see index is 255. Here, this is 150. All right, 200. So that's how much the red channel has, 200 in red. All right, so that's nice. We can kind of probe our image. But we can also probe that image with IMShow of, let's do IMShow of S. We can come in with this data tips tool and come in, just highlight over our color, and it's going to give us our RGB values, 0, 150, 255, right? For B, we're going to get 150, 0, 0, right? So all these things, we just kind of pop up the colors that we want. So if we want to mask out certain colors, we can come in, IMShow, and then go with our data selection tool up here, and we can click over and see what that color corresponds to.